Okay, I want to do another example. This one should hopefully go faster. This is something I did in class, so I'm just going to sort of review it. I think you guys have probably seen it a couple times. But this is actually problem 16 or problem 6, depending on how you look at it, on the review packet. So, the problem is you have an infinite line of charge, or call it like an infinite wire of charge, you might think. So I'm going to draw, let's see, I'm going to draw that as a, let's do that as an orange line. No, let's do it as a, oh, I don't know, I'm being too fussy here. Let's do it as a baby blue line. So here's your baby blue line of charge. You don't know if it's positive or negative, but you do know it's an infinite line. It goes in both directions. So it goes infinitely in both directions, and there's some uniform distribution of charge on it. So what we have is what we call a charge density. Lambda is usually how that's written. And the way I like to think of lambda is that you have, say you pick a length L, you just chop out some arbitrary length out of this infinitely long thing here. Then the charge inside the section of the wire that's that length is Q, okay? And lambda is Q over L. So lambda tells you how many, say, how many coulombs of charge you have per meter or something like that. Okay, so what I want to do is use Gauss's law to solve this, hopefully quite a bit faster than I did in the last video with the sphere, because this should be, some of these techniques should be sort of old hat. So let's consider first the symmetry of the problem. So let's say here I'm looking end on at the line of charge. So this is like the line of charge is stabbing me, in the eye like that, okay? Or coming out of the page and stabbing you, or maybe you moved your head and didn't hit you, whatever. Okay, and let's say you are at a distance r from the charge. What is the electric field where you are? And so I guess I should specify before I jump into this. We did want to find the electric field at some distance r. So there's our r. We did want to find the electric field there. So the electric field is what? Okay. Or I want to find the magnitude of it. I mean, it should be kind of obvious. So at this point here, what do we expect the electric field to be? And you can remember from the previous thing how we did sort of our symmetry arguments about the sphere to explain that why we assumed, or why we could convince ourselves the electric field should always be going in or out. And so I'm going to do the same thing here by saying that the electric field, you can't, a solution where the electric field goes along the charge line, or where it goes like in a direction perpendicular to the line, that's also perpendicular to R, so like coming up out of the screen at you, for example, if R is going this way, doesn't make sense. So if you're like, say here, and say this is the line of charge coming at you, an answer where the electric field is also coming out at you, or so like this for the electric field, this is a charge coming at you, or a vector going at you, or a vector going away. These ones don't work, and a vector that's going perpendicular, an electric field vector that's going perpendicular R, or that way, also doesn't work. So these are all no, 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 no. Okay? So what we know now is that the electric field has to be going one of two directions, straight out or straight in. And so from before, we're going to take our same formulation and say the electric field here is going to be equal to some scalar number E times R hat. And R hat is your unit vector going in or out from R. Okay? So at any point, and it could be different for different values of R. We're reserving that right. But for now, we can say at least that it must go in the direction either straight toward or straight away from the line of charge, perpendicular to it. No other options. So what kind of Gaussian surface do we want to draw? Well, we need surfaces where E dot n hat is constant. But here's the trick. We don't have to have like one smooth surface to encompass this whole thing. What we need is some set of surfaces we can piece together into a complete closed surface. And those sets of each of those surfaces and the set of surfaces needs to have a constant E dot n hat, but they don't all need to have the same one. So we can take, for example, a surface where the electric field is parallel, and so E dot n hat is 0, and we can take a surface where they're constant, not this product is constant, not zero. Piece them together, and then just add this up sort of piecewise by each area, and you'll see how it works in a second when I get there. So remember how before we pointed out with the sphere we could, if we had these surfaces where E dot n hat was zero, that meant surfaces that slice straight through. Sorry, clean the mouse thing. Surfaces that slice straight through our point of charge. Well, here, if you take, so I'm drawing in the electric field here at various points, always the direction of it. Here, if we take surfaces that go the same direction as the charge, those will slice right through our line, and we can actually very conveniently use those right here on the ends of our length L to sort of, chop it off there, as it were, and then we just need something to connect these guys. So we can basically build any shaped wall we want here, as long as it's all parallel to the electric field, which means it's perpendicular to this line of charge. So then, what kind of surface do we want to connect these to? And, again, with a moment of thought, it's not hard to figure out that what you want is a cylinder. We want to, so here's our end-on view I'm going to look at for a second. And we want to have a bunch of points where R is the same, because, again, the symmetry of the problem argues for us that it doesn't make sense to have different electric field magnitudes at different distances from the center, right? So what we've found now is that E is definitely dependent on R, and we can count on the same magnitude electric field at all these points on the cylinder. Now, it could be different, different directions, obviously. In fact, it has to be, but we know it's going to be the same magnitude. So at any of these points, the electric field vector is going to equal some scalar times R hat. Okay, great. So we're going to close this off. We're going to turn this into a closed cylinder. Now we need to do this over every surface of the cylinder. And so we have, flux for the cylinder is going to equal flux for, so we have the left end cap, I'm going to write L cap here, okay? And plus flux for the right cap, I'm going to write R cap there, plus flux for this curved surface in the middle, which I'm going to call the tube, okay? So we need to do the flux for each of these three. Now remember, here we pointed out, and so again, flux is E dot n hat. We pointed out here, again, that the field is always going parallel to the end caps, and that means that E dot n hat is going to be zero. Let me just draw an n hat there to make this clear. So our electric field vectors are always pointing this way, pointing up this way or down this way, okay? And then n hat is pointing that way for these end caps, right? So at any point here, no matter where it is, this dot product is going to be zero. So this is going to equal, for the left cap, total flux is going to be zero, because you're just taking 0 times the area, right? And it's going to be 0 for the right end cap. So what is it now for the tube? On the tube, which I'm calling the sort of the tubular, this rounded surface, E dot n hat is going to equal E r hat dot n hat. Now again, which way is r hat going? Well, these blue lines show the direction of r hat, right? Because E points the direction of r hat. Which way is the normal vector on the surface? Well, again, it's like the cylinder; it's always pointing outward. Anywhere on this tube, the normal vector and r hat point in the same direction. So again, these are unit vectors pointing in the same direction, which means that dot product just becomes 1, which means E dot n hat is just equal to E on the tube. So here, our E dot n hat times A for the tube is just E, and then the area of the tube, which is the circumference of this times the length of the tube. So this is the end cap, and this is the diagram of the end cap. So you imagine this is like a Pillsbury cookie dough roll, and you have to peel the label off before you pop it. And so the length of the label in one direction is 2 pi r, and the length in the other direction is L, the length of the cylinder. So 2 pi r L. And scroll down just a little bit. Okay, so that is our phi for the cylinder. Phi for the cylinder is E times 2 pi r L. And by, I have to scroll back up now, Gauss's law, we can either make that equal to Q net times 4 pi k or Q over epsilon naught. And it's not hard to see then that it's easier to use 4 pi k Q net So these cancel, and Q then is our the amount of charge we had in here, whatever it was. L is the length of this thing, whatever it was, but we know a relationship between those two. And so if we want to find the magnitude electric field, we take let's see, so we're going to divide the 2 pi through. That's going to be 2 times K times Q over R times L. Well, and so finally, we take this Q over L, and that's our definition of lambda. So usually you're given lambda here, and I happen to have an easier time doing it with Q and L, so I just sort of make up a Q and L, plug them in, and then when they come out at the end, they come out to be in terms of Q over L, and so that's the way I do it. E equals 2K lambda over R. And then if we want to go back, and find an actual electric field vector, we just take this and apply it. And so we do hat, put that on top, and then we are done. So what we found is the electric field vector always points away. It's the magnitude is here 2k times the charge density per unit length. And what's interesting about it is that we find it in terms of, or we find that it only falls off like 1 over r instead of 1 over r squared. So remember, for a point charge, electric field was kq over r squared. Here we have this. And so it's interesting when you get something that's infinitely stretched out in one direction, the electric field actually only falls off like 1 over r instead of 1 over r squared. Okay, so there you go. There's your answer. And then I'll do a surface very briefly in one more very short video just to sketch out how